Okay, so for this one, we're supposed to find the product of sums form using a Carnot map. So everything in digital logic, you have duals. So if you have something that works with products, you have something similar that works with sums. And if you remember when you had your theorems always came in pairs. You always had these duals. And so if we had a way to do Carnot maps with sum of products, there's going to be a way to do it with product of sums, but you can bet that pretty much everything is going to be backwards. So first of all, it's not going to use min terms, it's going to use max terms. So the first thing I want to do is rewrite this as the product of max terms. I don't have to. Okay, so I don't have to. So I will, but I'm not going to end up using them. This is just to show that we could. So it'll be 0, 1, 2, 3, 4, 5, 6, 7. The main reason for doing that is to see, is one of these easier to work with than the other? Because if one of them has fewer ones, if we're working with min terms, we need the ones. If we're working with max terms, we need the zeros. If one of these had one variable and the other one had 7, we would clearly want to do the one that had one variable. But here, they're pretty much the same, so it doesn't matter. So I'm going to, but we have not, up until this point, filled in the Carnot map with just ones or just zeros, and we can do that. You don't have to fill in both of them if you don't need both of them. I'm going to fill in the min terms. So the way the boxes are numbered, you can get the box number either by looking at the binary number that is represented by the 3 variables that make up the box, or it's numbered like this. You start with the top with a 0, and then 1, and then you go to the next column, you get 2, 3, and then remember we swapped over the last 2, so then you jump over to the last column, and you get 4, 5, and then you come back to the column that we skipped and we get 6, 7. So if I have min terms 1, 2, 3, and 5, that means I'd have a 1 in 1, 2, 3, and 5. That means that I have zeros in 0, 4, 6, and 7. So since I'm doing product of sums, I need the zeros. And so I didn't have to write the ones if I didn't want to. I could have just written the zeros. But I just wanted to show that if we write the ones, we can get the zeros either, the zeros are the ones that don't have ones in them. So now I want to cover these zeros. So I think I see 2 groups of 2 is the best way to do this one. I think this and that. Do you see anything better? Okay. Now, remember, this is the dual of the way we were doing it before, so everything is going to be backwards. So in this column, it has x1 is 1 and x2 is 1. That means I'm going to have x1 bar plus x2 bar. So if everything is opposite, if the ones become barred and the times, or the and becomes an or. So that group is x1 bar or x2 bar, and the group off that goes across is going to be, what do they have in common? They have an x2 equal to 0 and an x3 equal to 0. So that will be x2 or x3. Now just for fun, let's verify that that's what we would get from the sum of products. If I multiply this out, I would get x1 bar x2 plus x1 bar x3 plus x2 bar x2 plus x2 bar x3. So x2 bar x2, that is 0, and x1 bar x2, x1 bar x3, x2 bar x3, this is the same. These are complements. And this is the same. And so I believe that means we can make this, I'm trying to remember which one this is. I think it is, because I'm pretty sure we should get, no, but maybe it's not. Go, okay. Because what we would get with the ones is we would get this group and this group. So that would give us x1, so this column is x1 bar x2 plus, and this group right here is x2 bar x3. Yeah. So let's see if I can remember the rule. It's x1, let me just, for x, y, plus let me just pull it up. You don't happen to have the theorems handy? Okay, excellent. So this is xy plus xy plus yz plus x bar z. So equals, be important to know what that equals xy plus x bar z. Okay, so if you have on two of these, you have the variable and its complement, and that's on two of them. And then with one of those and the other one, you have the same variable, and then you also have the same variable here. So you have these three terms, and two of the terms share one variable. In this case, it's a y. And two of the terms, not the same two, share another variable, and that one's a z. And then the variable that's not shared has to be the complement. And so, and then the one that can drop out is the one that has the shared variables. And so with what we have here, I have x1 bar and x1 bar, that's shared. I have x3 and x3, that's shared. And then I have x2 and x2 bar. So the variables that were shared were x1 bar and x3. So the one that has just an x1 bar and an x3, that one can drop out. And does that match what we have over here? It does. Okay, now we're going to talk about something called don't cares. So there are times when you are building a circuit when you have certain parts that you don't care about because they're never going to occur. The way the circuit is set up is, it's never going to happen that you would have that particular condition. And when you have those things, they're called don't cares, and it can lead to being able to build a simpler circuit than if you restricted those don't cares to being a certain value. So we'll see how to do that. So first we'll draw a Carnot map. This is a 3-variable Carnot map for x1, x2, and x3. Shift the top. Okay. So we're going to get to Verilog. And I fill in the min terms. Well, let me number my squares. So 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. I'll tell you what messes me up, because in computers, you always start counting with 0, always, except for MATLAB. And I'll be working with MATLAB before too long. MATLAB starts counting with 1, and it drives me crazy, and I've been working with MATLAB a lot lately. If you pick up the handout that I posted on the website, you'll see that I put on it I guess I could have just opened up the handout from my own computer. And so this is worksheet 3 Verilog and K-maps. At least I hope I put it on here. I did not. Is that as far as it goes? Yours? Oh, there he goes. Okay. Okay. If you look on the last page, I have set up for you, first of all, for what the min terms are. And so we have M0, M1, M2, M3, M4. And so this corresponds to when there's zeros, the variables are knotted. And so like this one right here, M3. Oh, I can't draw on it because it's, okay. M3 would be x1 bar, x2, x3. And if I needed the corresponding max term, it's exactly the opposite. It would be x1 plus x2 bar plus x3. And then here's a Carnot map showing what min terms go in which squares. And then here is a 4-variable Carnot map showing what variables go in which squares. And if you look at how it's counted, you go 0, 1, and then jump down to the bottom for 2, 3, 4, 5, jump down to the bottom 6, 7, then jump over to the right 8, 9, jump to the bottom 10, 11, then go back to middle 12, 13, jump to the bottom 14, 15. And then I made a little chart for you so that you could see, well, what is min term 11? Well, min term 11 is x1, x2 bar, x3, x4. So you have that as a resource. And I would have that handy for when you take your test, so that way, even if you can do it on your own, you don't have to think about it, and you don't have to waste time and worry about if you're getting it right or not. Next test, I will be careful and pay attention and make sure that I know that y'all are having a test, and I will put together a little packet for you. Okay, so min terms 1, 4, and 7. So 1, 4, and 7, and don't cares on 2 and 5. Now the thing with don't cares is don't cares can be either ones or zeros, and you use them if they help you, and if they don't help you, don't use them. So you can use them as ones, or you can use them as zeros, but you don't have to cover them. So it's not necessary to cover them. So on this one right here, it is useful for me to use this don't care to make that a bigger group. And it is useful for me, I think I have to use 3 circles on this one. So I'll get that one, and I'll get that one. I don't see a way. It seems like I should be able to do it with only 2 circles, but I don't see a way to do it. A lot of times people will ask me, well, can't you get these? And the answer is no, you can't, because that's a group of 3. It has to be a group of 2, 4, or 8, or just 1. Now what this did for us is we have 3 groups of 2. If we couldn't use the don't cares, we would have 3 groups of 1. And in a 3 variable Carnot map, a group of 1 has 3 variables in it. So if I just used those, I would have x1 bar, x2 bar, x3, or this is not the simple answer, this is not the minimum form, I'm just showing you what it would be, plus x1, x2, x3, plus x1, x2 bar, x3 bar. That's what you would get if you couldn't use the don't cares. But with the don't cares, this group wrapping around right here has x2 in common is x2 bar, and it has x3 in common. Plus, this group has x1 in common and x3 in common, and this group has x1, x2 bar. So this function is more minimum than this one. It has 3 AND gates and 2 OR gates, but our AND gates are only 2 variable AND gates and not 3 variable AND gates. So this one, just ask yourself which one would I rather draw. Okay, so I think I'll do, and it said also minimum product of sums. So to do product of sums, I'm going to redraw it. And I'm going to put in the zeros, so I'll have zeros everywhere I don't have a 1 and don't have a don't care. So to do product of sums, I have to cover all of my zeros, and it looks like I would get this group, and this group. And that would equal this group right there would be x1 or x3. This group is going to be x2 bar or x3. And our last group, the vertical group, will be x1 or not x2. So this one has, this one had one 3 variable OR gate and 3 2-variable AND gates. This one has one 3 variable AND gate and 3 2-variable OR gates, so same cost. Okay, I'm going to stop here.